Today I start one important theorem related to this Banach space. Okay, and obviously this one related to quotient space. We also previously we done some quotient space with Banach space, and obviously first we discuss some definition nouns quotient space with noun space and quotient space with Banach space, and one given condition is y be a closed subspace of X. Okay, this one is needed for that. So now we discuss another one. Now we discuss one important topics related to this, and obviously this one is, that means y be a closed subspace of a noun space and quotient space be Banach space, then this given space X be Banach space. How this one is happen? I think this one is easy from previous one, but we do it. Okay, let y be a closed subspace of a noun space, and let let y be a closed subspace of a noun space X norm, and let X norm be a Banach space, then X is a Banach space. Okay, so we have to prove this portion. Okay, obviously we write proof here. So we start about that. That means we have to show that. First we write this one. We have to show that X be a Banach space, that is X be complete, and for this let Xn be a Cauchy sequence in X. Then this one, okay, this one equal to what? This one equal to here xm difference xn norm x quotient y. Okay, for all mn belongs to this natural number, equal to what? Equal to infimum of y belongs to y, here xm difference xn plus y. Okay, this less than equal to norm of xm difference xn. Okay, now again we erase our portion and going to further discussion about that. since x n be Cauchy, since x n be Cauchy in x, and it follows that this one box x n be Cauchy in x quotient y. Okay, then what happened? Since x quotient y be a Banach space, then what happened? Then limit n tending to infinity, norm of class of xn equal to this one class x. Okay, this quotient space. Since x quotient y be Banach space is given. Okay, then what happened? Let epsilon greater than 0 be given. Since this class going to x, then what happened? Then there exists n0 belongs to this natural number such that norm of xn difference, norm of x, here x different quotient y less than epsilon for all n greater than equal to n0. Okay, now this implies that infimum of y belongs to this one, norm of xn difference x plus y. Okay, this less than epsilon for all n greater than equal to n0. Okay, then what happened? Then thus xn difference x plus yn be convergent to 0, be convergent to 0 belongs to this x. Okay, then what happened? Since xn be Cauchy, okay, we now erase our portion and going to further discussion of that. Now we erase that portion, okay, and going to further discussion of that. So what happened here? Here obviously we see that then here this one infimum of y belongs to y, okay, norm of xn difference x plus y less than epsilon for all n greater than equal to n0. Okay, then what happened? Then there exists a sequence, okay, then there exists a sequence yn in x such that mod of x n difference x plus y n less than epsilon for all n greater than equal to n0. Okay, thus what happened? Thus this one x n difference x plus y n converges to 0, converges to 0, belongs to x. Since xn be Cauchy, since xn be Cauchy, okay, and xn difference x plus yn be Cauchy, it follows that yn be Cauchy. Okay, now that means this one, how this one happened, we also see these things in this way. That means this one is not do it in this way, but we write it, that means in short. Here this one xm difference xm less than epsilon, here xn difference x plus yn, sorry, this one difference xm difference x plus yn less than epsilon. Okay, so we mark those. Then here what happened? Xn difference xm plus yn difference yn less than epsilon. Okay, so if we write here in this way, that means yn difference ym, okay, this one less than equal to what? Equal to in this way xn difference xm, okay, plus xn difference xm plus yn difference yn, and this less than equal to xn, this less than equal to what? This less than equal to, we erase that portion, then this one happened, this one, this less than equal to xn difference xm plus xn difference xm plus yn difference yn, and this epsilon plus epsilon equal to 2 epsilon. Okay, so y be Cauchy. Now what happened? Now in this way we see that means yn is convergent. Okay, since yn is Cauchy, and obviously that means without loss of generality, okay, we may assume that yn converges to y belongs to this y. Since y is closed, okay, that means this sequence converges to y, and this obviously belongs to y. So what happened? So we write here, note that x belongs to x and y belongs to y. This implies that x difference y belongs to x. Okay, so what happened? So we write again this one happened, xn difference x plus yn converges to 0 and yn converges to y. This implies that xn converges to x difference y belongs to this x. Okay, so what happened? So this one, that means this one how happened, we write here in above x, that means this one belongs to x, and this one tends to 0, and yn tends to y. Okay, so that is how we discussed about this one. Here this x n difference x plus y n mod difference 0 less than epsilon. Okay, we write it another that means we just write it in another color pen. Okay, so here in this way, x n difference x plus y n less than epsilon, and here y n difference y less than epsilon. So x n difference x difference y, okay, or difference this one equal to x n difference x, okay, plus y equal to x n difference x plus y n, okay, plus y n here plus here plus y minus y n. Okay, then what happened? Then this less than equal to x n difference x plus y n plus y n difference y. This less than epsilon plus epsilon equal to 2 epsilon. Okay, so we erase that portion and going to further discussion of that. This implies what? This implies this portion here x be a Banach space. So what we discussed today, obviously y be a closed subspace of a norm space x norm, and x quotient y be a Banach space. Then we proved that x be a Banach space. How we prove? First we considered some Cauchy sequence, and then we saw that that means this Cauchy, that means this element of in quotient space obviously form a Cauchy sequence. Okay, that means xn Cauchy, so class of xn is Cauchy in this quotient space. Okay, then since x quotient y be Banach space, so this class of xn obviously convergent. Then we show some definition of this, and going to be proved that xn difference x plus yn be convergent to converge to 0, and then again xn Cauchy and this one Cauchy, so yn Cauchy, and without loss of generative y1 belongs to tends to converge to y belongs to y because y be a closed subspace. Here we write this one is better here since y closed. Okay, then what happened? Then note that x belongs to x and y belongs to y, and x difference y belongs to x. Okay, so this implies that xn difference x belongs to yn and yn converges to y, so xn converges to x difference y, so x be a Banach space. Okay, not a problem at all. Now we stop here. If you get this type of video, obviously that means you subscribe my channel, and if you like this type of video, then please give like, and if you have any questions, write it in comment box, and any suggestion about that, then write it in comment box. Okay, so today I stop here.